Hello, my name is Eugene Koifman. I work at Hortonworks, where I'm a tech lead on the Apache Hive asset project. So today I'm going to talk to you about the state of the project. So first, I'll go over some history and explain why we decided to build it and what the main goals of the project were. Then I'm going to talk about the high-level feature set and what it looks like from the end-user point of view. And then I'm going to describe the architecture and what it takes to implement this feature set on top of Hadoop. And then I'm going to talk about the recent progress and what we're thinking of doing in the future. So first of all, why do we think this was necessary to build? The easiest way to explain that is to first go over a couple of use cases of how you were able to do these things before these features were available, and I think that will make it clear. So the first case is, let's suppose you needed to add data into your Hive tables continuously. So what were your options? You could stage the data into a temporary table and then run an insert statement into the target table. Another possibility was to, again, stage the data in some temporary table and then run a statement to add a partition. Both of these approaches have similar drawbacks. If you perform these operations very frequently, then you end up creating lots of small files, and in case of partitions, lots of small directories, and that affects performance negatively, and in the long run, it creates pressure on the name node and the Hive metastore. Alternatively, you could have run these operations less frequently, once a day, perhaps once a week. That solves the problem of small files, but then it creates a different problem because your end users now have to wait longer before they're able to see the most recent data that should logically be in the table. The other important case is modifying existing data. Now, if you're using Hive to primarily analyze log files, this may not be so important because they're essentially static. Once they're ingested into Hive, they never have to change. On the other hand, if you're, for example, offloading the data from some operational data store, then ability to delete some data later, for example, for legal reasons, or to update the data once it's been written because of potential, some mistake in the source system, that may be very important. So really the only option that you used to have is to use an insert override statement, and let's assume you're trying to delete some data. So you could write this insert override statement with a select clause that filters out all the rows that you no longer need, and then overwrite the target table. Now, that works functionally, but if you need to perform this operation often, especially concurrently, then you can be in trouble because multiple operations, one can override the result of the other, and you're not certain what the final state of the system is. Now, one way you could have dealt with that is to use a zookeeper log manager. Now, this log manager has a kind of restrictive model where it allows you to, it either has shared or exclusive logs. So if you're running, if there is a long-running query running over the partition, then you can't run your update operations and vice versa. Also, if you're actually just trying to modify, let's say, 1% of your partition, overriding the entire partition if you have to do this repeatedly, gets expensive on the right side. So the reason that we built this project is to make these kind of use cases easy and efficient in Hive. One of the key constraints in the system is to make sure that, since Hive is often used for long-running analytics type queries, you want to make sure that these queries are able to proceed while concurrent update operations, so that they're not blocked by the concurrent update operations and vice versa. Now, one sort of disclaimer, the system is designed for slowly changing tables, so it's in no way an OLTP system. So that means if you, for example, have run a single transaction that modifies 1 million rows, that's fine, that's going to perform well. If you try to run 1,000 concurrent update statements, each of which match 1,000 rows, that's not going to work well. So the features of the project at a high level is, first of all, we added the support for a new type of table that supports these insert, update, and delete SQL operations. Secondly, we introduced the concept of an ACID transaction to Hive. ACID is an acronym. It stands for atomic, consistent, isolated, and durable. And the main reason for this is that it brings order to a system where things are happening concurrently. It's in some ways similar to, for example, the synchronized keyword in Java multi-threaded programming. And it makes the system transition from the transitions of the system from one consistent state into another consistent state well defined. And the third major feature is the streaming ingest API that allows you to continuously write a stream of events into an asset table with transactional semantics. So at a high level, we distinguish between two types of clients. There is the SQL client, so for example, the Hive CLI or Beeline, and the streaming client. Now, so when the request comes into the, or when the request is made by SQL client, it communicates with the Hive metastore to demarcate the transaction. Now, in return, it receives the transaction ID, and also all the data generated as a result of that operation is tagged with this transaction ID. Now, this is important when we later read the data to figure out sort of which data was created by which transaction. Streaming client sort of similarly talks to the metastore to obtain a transaction ID, though in this case it writes directly to HDFS. So at a high level, from the end user point of view, the first bullet point that you see there is the simplest way you can create a transactional table. Now, the first thing to notice is this transactional equals true property. So that means that not all tables have this property, and you have to opt into this set of features. Now, the second thing to point out is this cluster by clause. So that's basically a high way of saying that the table has to be hash partitioned into some number of buckets. Now, this is not to be confused with Hive partitioning, which is partitions data by value. Now, this is important for performance because it allows us to figure out whether a given row has been updated and to find the later version of that row very easily. Now, the next thing is that the table cannot be sorted because the implementation of the system requires this table to be sorted in a specific ways for us to be able to materialize the data more efficiently. So you as the user cannot add any sort order to the table. In order to support these set of features, there are significant demands on the storage layer for this to work. And this is encapsulated in ACID input format and ACID output format interfaces. So as long as the input and output format of the table that you're using implements these interfaces, that can plug into the system. Now, at the moment, workfile is the storage format that has implemented these interfaces. In terms of the semantics that we provide for the read operations is snapshot isolation. So what that means is that whenever a read request comes into the system, it, logically speaking, locks in the state of the database as it existed at this moment in time. And so this read operation sees the results of every transaction that committed before this moment, but is not affected by any transactions that commit while the query is running. Another important thing to point out is that in the current implementation, everything is in auto-commit mode. So that means you as the user cannot issue begin transaction statements or commit, and every statement is essentially its own transaction, though that will change. So now let me talk a little bit about what it takes to implement this. And so the first major enhancement that we had to do is introduce multi-version concurrency control architecture into the storage layer. And so what that means is that the system is able to keep track of multiple versions of each row at the same time. And this is the key sort of design feature that allows these long-running analytics types queries to proceed while a concurrent update operation can also make progress, and neither one is blocked by the other. The other important aspect of the system is what do we actually do with the data that's produced by all of these write operations. And so HDFS is an append-only file system. So that means once you actually write the data into it, you cannot go back and modify something in the middle of the file. So the results of the update operations or any write operations are stored in what is called a delta file. Then at read time, these delta files are combined together to produce the snapshot relevant for the particular reader, or which is correct for the particular reader. Now, even if HDFS did allow you to update a file in the middle, we'd still go with this design choice. And the reason is that for analytics types of workload, the architecture of choice is some sort of columnar storage format, which is what ORCFile provides. And it stores, it's very much a format that's optimized for read operations. It reorganizes the data, not in row by row format, but it compresses it by column, which provides a lot of efficiency, which makes the read operations later more efficient, but it makes updating that data in place more difficult. So that's another reason why the data first has to be written to the side file and then merged together on demand. So now I'd like to go through kind of a simple contrived example of a few operations on the system, and I think that will make these ideas more concrete. So the simplest way to create, So the simplest way to create a transactional table is the first bullet point here. One thing to point out is that in this example, it has a bucket count of 1. Probably never want to do this in real life, but it makes the example simpler. So suppose you started with the table that only has 2 rows, and here you see the values of these. Then let's assume you ran 2 update statements, and each of these update statements matches exactly 1 row. So the modified data is -1, 2, and -3, 4. So what's useful to do is to take a look at the contents of the file system and sort of to see how the data is actually organized in the storage layer. So here you see a very kind of sanitized example of the files that make up the data for this table. And so the first thing to notice is a base file. So this is what this is where the data for the table was before we run any of the update statements. Now you also notice the 2 delta files, each of which was created by the corresponding update statement. You also notice that the bucket file, this is where the data actually is, but because we created a table with a single bucket, you only see 1 file. If you had 16 buckets, you'd see 16 files. One important thing is what are these numbers and the names of the directories. So the numbers are transaction IDs, and this is what allows us to easily figure out which set of files to pay attention for any particular reader. So here's a look at what the data looks like. This is there is a utility in Hive that allows you to print out the data in an ORC file in this JSON format. The actual storage format. The actual storage is, of course, binary. So here on your right, you see the actual values in your table. So here's the contents of the base file, and here is the contents of one of the Delta directories. So the key thing to notice is this underlying portion. So when data is first ingested into a table, every row gets assigned a unique primary key. And this primary key consists of 3 values. It consists of the original transaction, which is the row that, or the transaction that initially created the row, then the bucket ID, which is where the row hashed to, and the row ID is essentially sequential numbering of the rows for a given transaction and bucket combination. Now, in the Delta file, you see sort of the same primary key, and this is how we match up the rows between the base file and the Delta files. Now, I mentioned earlier that the data in these transactional tables has to be sorted. So it is sorted by this primary key because in order to materialize the snapshot at read time, we perform something that's rather similar to a SQL join operation. So it joins all of the base file to all of the Delta files, and having the data sorted according to this primary key makes the operation more efficient. And so here is an example based, it's formatted a little bit strange, but anyway, it's based on the data that you saw in the previous slide. So here the merge process, so it's a hypothetical select star from T query that shows you how this join process works. One thing to point out is that here the This is an example that's showing when a select request came into the system after transaction 24 has already committed. If, for example, the request landed in the system while this operation was still being performed, then the system would know to simply exclude any operation performed by the transaction that hasn't yet committed. So the next major module in the system is the compactor. So as more and more of these modification operations happen in the system, more and more of these Delta files get created. So that makes the operations on read, the merge process that we have to perform on read, more and more expensive. So in order to compensate for that, the system has a compaction process. It's a process that runs in the background and constantly rewrites your table. And there are two types of compactions. There is a major compaction and a minor compaction. So minor compaction simply combines several Delta files into a single Delta file. Again, so that makes the merge process cheaper. And the major compaction combines the base file with whatever Delta files are currently in the system. The major compaction is a lot more expensive since on average, you expect the bulk of the data in the table to be in your base files and only the recently added data or the recently modified data to be in the Delta files. One other useful property of this compaction process is that it makes essentially work files more efficient. As you initially write the data into the system, for example, if you're using streaming API, you may be calling commit frequently because this is what the logic of your application dictates. But that creates small stripes in the work file, which makes work less efficient. But as the compaction process keeps rewriting the table, it will make larger stripes, which makes better compression and more efficient use of the, or makes the indexes more useful that work maintains. Now, a compaction process can be triggered on demand by running a command at the CLI, but usually you want to let the system, it can also be triggered automatically by the system. There are various configuration options that allow you to control when exactly that happens. Another important thing to note is that compaction consists of several lightweight processes running inside the metastore, the Hive metastore, but the actual compaction itself is a MapReduce job, so it runs on the cluster. Now, one of the, really important design principles of the compaction process is so that it does not in any way interfere with your ongoing operations on the tables, whether it's reads or writes. It does not acquire any logs. It does, however, take up some cluster resources. Now, as these files get written and rewritten, some of them become obsolete, and so there is an additional cleaner process that figures out when it is appropriate to delete these files. So I keep talking about things happening in parallel. So that means there ought to be something in the system that actually manages this concurrency, ensures that things execute correctly. So the two modules that are responsible for that is the transaction manager and the lock manager. The transaction manager is responsible for assigning transaction IDs and keeping track of the state of each transaction, whether it's open, committed, or aborted. Additionally, it keeps track what each transaction has modified, and that's later used for several reasons. One reason that it's needed is to drive the compaction process. This allows the compaction process to decide whether it's worth running a compaction on a given partition. Another thing I should have mentioned, compaction either runs on the entire table if the table is unpartitioned, or on one partition at a time for partition tables. And the other reason why we need to keep track of what each transaction modified is to prevent write-write conflicts. So if you have two concurrent update operations, you want to make sure that they don't end up updating the same piece of data at the same time. That causes lost update problems and essentially sort of creates incorrect data. So so preventing these kind of conflicts is implemented using write-set tracking. And what happens is at commit time, the current transaction checks with any past transaction that overlapped with it in time, and to look at what data the other transactions have modified, and if there is any overlap, then the current transaction is unable to commit. It's usually called the first committer wins rule. One more thing to point out is that while two concurrent update operations can be in conflict, in Hive, two concurrent insert operations are never in conflict, and so the reason for that is that Hive doesn't have any way of enforcing unique constraints. Two rows that may look identical from the user point of view will each get assigned a unique primary key. So as far as Hive is concerned, these are separate rows. You are able to, in a single read query, combine ACID and non-ACID tables. That works fine. You cannot, from a single transaction, update table, combine updates to tables that are ACID and to tables that are non-ACID. And the reason for that is that these transactional tables, they're smart enough to to know that if the transaction fails in the middle, then it will never return any partial data that this transaction may have written. On the other hand, for non-ACID tables, they don't have that logic, so that again could create incorrect results. I don't actually know if that's enforced at the moment, but probably something something you shouldn't do. So the next high-level feature of the system is streaming ingest. This is a set of APIs that allow you to continuously write a stream of events into a Hive table with transactional semantics. And so this is implemented in such a way that you can reasonably, so in this system, you can call commit operations on the data to make a particular set of events visible and durable in the system. So it's implemented in a way where you can call these commits frequently enough. You can do this every minute, maybe even every second. But the implementation is such that it's able to combine multiple transactions in the same file, and thus avoiding this explosion of little files that cause performance problems later. Now, this API only supports adding new data. You cannot execute any kind of update commands to existing data. The API itself can be used directly, but it can also be used from tools like Storm and Flume, which have implemented adapters that leverage this API to stream data into Hive. So now let me talk a little bit about recent improvements that we've done in the project. So Work is a smart storage layer. So it has a feature where it can execute predicates from the query. And so by evaluating the predicate, it can limit dramatically the amount of data that it needs to read off of disk to materialize the query. The original implementation had only very limited support for this predicate pushdown. It only worked on the base files. We support it in a lot of cases for the Delta files, and hopefully within days, some changes should land that will support it for basically in any situation, in any query over an ACID table. Another important feature is the schema evolution. It has evolved to the point where it works with ACID tables, and you can actually run alter table commands to add columns to the ACID tables. We've improved split computations. We used to run into some situations where the query plan ended up with very low degree of parallelism and thus hurting performance, so that's been addressed. A lot of effort went into usability. So, for example, there is a show compactions command which allows you to see the state of current compactions in the system. It only used to show the currently running compactions. Now there is a configurable retention period for past compaction jobs, which is also useful. Show logs command, which is something that shows you the state of the log manager at the moment, that's been enhanced to show, for example, if some log is blocked and waiting for some resource, it'll actually tell you what resource it's waiting for. So if some operation that you're running is blocked for unknown reason, you can actually use this command to figure out what other query potentially is blocking this. It also includes information who issued the lock request. So it makes the system easier to use. We've introduced a number of safety checks into the system. So one example would be you could misconfigure the system in such a way that would, especially in the streaming client, in the streaming use cases, where it would potentially open up millions of transactions in the space of a few minutes, all of which would be empty, but the system is certainly not designed to handle that. That would kind of create too much metadata for the system to handle. So things, improvements of that nature have also been done. These processes that run inside the Metastore that make up the compaction module, there used to be a requirement that they have to run in one single instance of the Metastore, which makes HA setup more difficult and also makes the configuration more difficult. So now they've been made more intelligent, where they can run in any number of Metastores, so you get better HA and easier configuration. Metastore scalability have received a lot of attention. The Metastore side that supports operations related to ACID queries could potentially lock up fairly easily under concurrency. So spend a lot of time improving that, improving the scalability of the Metastore. Any number of bug fixes across Hive, Flume, and Storm to make all these three systems work better together. So now let me talk a little bit about what we're hoping to accomplish in the future. Keep in mind that it's a forward-looking statement, so it may not work out exactly this way. Dynamic bucketing. As I mentioned before, these tables require you to specify how many buckets the table should have. That is, it's not always obvious what the correct answer here is. For a smaller table, let's say 100 gigabytes, maybe 8 buckets or 16 buckets should be fine to have enough parallelism in some of the processes that support these tables. Now, if the table is several terabytes, then you probably want several hundred buckets to get adequate performance. So of course, if you're dealing with a table in, I don't know, streaming ingest, you start with an empty table, and a year later it has several terabytes of data. There's no good way for you to change that. So one thing that we'd like to do is to make this dynamic so that the system manages that automatically. Support for merge statement. So merge statement is part of the SQL standard, and it's in a way, it's like a very fancy update statement. So a regular update statement, you specify a where clause, and every row that is matched will get updated the same way. So here, it's logically speaking, it's as if you're able to combine any number of these update statements, and each will modify some set of rows in a different way, but it runs all as a single statement. Performance is, it's that's something that's forever a feature. Some of the improvements that we'd like to make is the current system can make heavy use of network in the cluster when materializing these snapshots. There are various things that we can do to reduce network requirements. Vectorization, some ACID queries vectorize better than others, but usually not as well as the non-ACID counterparts. So there are things that we can do here to improve this, which will improve performance significantly. Integrating with other subsystems, such as hcatalog, for example, this will allow Pig to read a transactionally consistent snapshot of Hive data. Integration with replication would be important. Completing the multi-statement transaction work, it's sort of 2/3 of the way done, but it's not quite ready for prime time. Concurrency, in the current system, the concurrency is very coarse-grained, and so that means that the system can sometimes generate false positives when it thinks that two concurrent transactions updated the same piece of data when in reality they haven't. So we can, there are ways we can improve that to make this conflict detection mechanism much more fine-grained. So better, again, improving usability is also one of the things we want to work on. So a few other things to add. Documentation, the first couple of links that you see here, this has detailed documentation, and if you want to follow the project and in more detail, here's a link to the Apache Jira system where you can track this at individual bug level, or if you'd like to contribute some fixes, please, you're very welcome. If you have questions, there is a user and a dev list that you can send questions there, somebody will answer them. And that's all I have. Thank you. Thank you.
I have a question on the basic compaction.